Okay, so for example number 8, we have to evaluate the integral from 0 to 3 and from x squared to 9 for the function x cubed e to the y cubed dy dx. All right, so if we wanted to evaluate this integral, so first with respect y, so we would need to evaluate this exponential e to the y cubed dy. But if we wanted to use the u substitution, we're missing a factor of y squared to stand the u du part of the problem, right? So we're screwed here. So we wouldn't be able to go about the integration in this order. So we would have to change the order of integration. Now, how do we go about? Is it just about simply the integral from x squared to 9 and from 0 to 3, blah, blah, blah? No, that's not how we change the limits of integration. This interchanging of orders works only if your region of integration is rectangular, all right? But in this case, this is not going to be a rectangular region. All right, so number 1, let's take the region of integration R, okay? That is all the order pairs x, y such that x varies between 0 and 3 and y varies between x squared and 9. All right, so we're going to use this to draw our region of integration. So let's go about the y's first and then the x's. So that means okay, y varies, okay, from the top along the horizontal line, y equals to 9, and below by x squared, that is 0, 0, 1, 1, 2, 4, and 3, 9. All right, so that is our, and for x, it's going to go between 0 and 3. All right, well, if you want to make this dash instead, or actually this is fine. Okay, so this is going to be our region of integration R. All right, so this will, let's shade. Of course, make sure to shade your regions of integration. And let's call this R. So, why do we need to have a look at the region of integration and also write it down as a domain? Because in this case, we will have to change the order of integration, but not by just interchanging the limits of the way we did it with the constant value. So here, okay, here we need to analyze the following. Is this region vertically simple? That is, do we have the horizontal line always at the top and the parabola always at the bottom within the interval we're integrating? Yes. Is it horizontally simple? That is, do we have the curve to the right and the vertical line to the left all the time? So yes, so it's going to work either way. Now the thing here is, okay, maybe a few more labelings here. That is y equals 9. This is y equals to x squared. And well, I think this is x equals to 0. I think this is good enough. All right, so when it comes to changing the limits of integration, we need to change all these functions in terms of the other variable. That means we need to come up with functions of y. So here, this is the same as saying x equals plus or minus the square root of y. But in this case, well, since we are only integrating over the right side of the parabola, we don't need the negative here. We only take the positive, right? So that is, simply take the positive. X equals to the square root of y. Okay, so now we're ready to set up the double integral. Let's write down the region of integration. So instead, I'm going to write R as the other way around. X, y, all the points x, y such that, okay, be careful here because now x is no longer varying between 0 and 3. X is varying this time between 0 and the square root of y. Also y is varying between 0 all the way at the top to 9. All right? So now we're going to write a double integral that finds that to evaluate this integral in the reverse order of integration. So this will be the double integral of x cubed e to the y cubed. That remains the same. Instead of going dy dx, we go dx dy. And we're going to go in the direction of x from 0 to the square root of y, and from 0 to 9 for the outermost limit. And again, this is still true because see how the inner limits are either constant values or expressions with the variable in terms of the outermost variable, which is y, right? So this is how we check for consistency about what we're doing. Okay, let's integrate with respect x. What's the integral of x cubed with respect x? That one is easy one, right? So 0 to 9. So that'll be x to the 4th over 4 e to the y cubed. This is just a multiple constant, and that goes between 0 and the square root of y, dy. And again, let me highlight the variable. So these limits of integration, 0 and root of y, are only taken in account for the variable x. Because we integrated with respect x, those limits are going to be evaluated only for the variable x. All right. Upper limit, let me take the 1/4 outside. That's a multiple constant from 0 to 9. X to the 4th. Well, actually, but yeah, that's fine. E to the y cubed. Dy, from 0 to root of y. Dy. So that is 1/4 integral from 0 to 9. Upper limit, which is root of y to the 4th minus 0 to the 4th e to the y cubed dy. Okay, square root of y raised to the 4th power, that's going to give us y squared. 0 squared, 0 to the 4th, it's simply 0, so that's going to leave us with 1/4 integral from 0 to 9 of y squared e to the y cubed dy. And well, by reversing the order of the integration, this is the magic that we needed to have that y squared factor so we can evaluate this integral using the u substitution, right? So do you see the problem here? In some cases, when it comes to double integrals, the way it's given may not be possible. We need to change the order of integration, come up with functions of y, and in this case, it's possible. All right, so u substitution. Let's call u equals to y cubed du equals 3y squared dy, y squared dy equals to 1/3 du. U of 0 equals 0 cubed, and u of 9 equals 9 cubed, which is going to be a big number, that is 729. So this 1/4 times the integral from no longer from 0 to 9, but from 0 to 729 of e to the u 1/3 du. Okay, let's simplify this double integral. 1/4 times 1/3, isn't that 1/12? So 1/12 integral from 0 to 729 e to the u du. Okay, the integral of e to the u is itself e to the u from 0 to 729, 1/12 e to the 729 minus e to the 0. And when it comes to these answers, these results don't raise the e to the 729. I don't think the calculator is going to be able to compute it for us, right? So otherwise, just leave it like this, leave it in exact form. That's 1/12 times e to the 729. At least do the e to the 0, which is 1. All right? So this is the result of evaluating this double integral, right? A good example of how we change the order of integration. All right. Well, so what do these integrals represent? Because if you notice, this integral we evaluated in this example does not have simply a 1 in the integrand. It has something other than a 1. It has a function of x or a function of y or a function of both variables x and y, which is this case right here. So what do these represent anyway? Well, so that's the next topic, volume. So in a similar way that we describe the area under the curve by chopping these regions these planar regions into infinitely many rectangles, what did we do for the double integral that represents the area? Didn't we chop into tiny squares of length delta x and width delta y? Well, that's to get the area of the region. Now, what are we going to do to find the volume in this case? Well, so you have a surface represented by z equals f of xy. So in this case, we're going to chop this region, or rather this solid, into not just rectangles, not just squares of length delta x delta y, but rather we're going to chop into rectangular boxes or square prisms of length delta x. This is our delta x with delta y and height delta z, if you will. All right, so what are we going to do? Find the volume, length times width times height. Find the volume and add the volume. Now see how we get an approximate result by chopping this solid into a finite number of these rectangular prisms, right? And well, do you see how it's not going to give us the actual result? Well, actually, this same GeoGebra project I have here, it's going to give us a good idea of how it looks like. Well, it takes a minute. Okay. So here, this describes the area below, right? The what we call the floor of the solid. I'm missing what's it called? Where's the other graphic? I guess I should open it again. Maybe. Definition. Yeah. Okay. Oops. For some reason it froze. Okay. Shoot. Okay. So here again, we have a domain of integration. It's a rectangular domain, but this time that function f of x, which is all f of x y or f of x or f of y simply, it's going to be the roof of the solid whose a floor is given by, well, in this case by a rectangular region. It doesn't have to be a rectangular every single time. So for instance, again, do you see these rectangular boxes right here? But do you see these corners outside of the surface? Though that's what makes the volume, not the actual result. The calculation, not the actual result. However, if we come up with a more refined result, that is by adding more, for real. Okay, by adding more, so it's crashing. Okay. So, okay, again, here we have these rectangles here, there's rectangular boxes there, but I'm going to come up with a better result by adding more of this rectangular. I'm going to add up all 20s. So do you see how it's a more refined solid? We don't have this corner this corner out of the surface as big as we had when we had less amount of rectangular boxes. Okay, let me do a lame one again. Let me do 4. Let me do a 4x4. So yeah, I think it's easy to see how inaccurate this result is versus 20 versus a 20 by 20 grid, right? Much better, right? It's the same idea as the rectangles that we chop the region under the curve, you know, and adding infinitely many of those areas of those rectangles. Same, adding infinitely many of the volumes of those rectangular boxes are going to add up to the actual volume of the solid. All right, so okay, close this and save. Let me go back to the notes. So here, now when we have a double integral, when the integrand it's no longer a 1, so that's going to be a volume integral. But again, just keep in mind that if f of x, y is simply a 1, that's going to be an area integral. All right? Okay, so let's have a look at one example. Find the volume of the solid that lies under the plane y plus z equals to 1, y equals to x squared, and the xy plane in the first octant. Well, there's a lot of information. Number one, the xy plane. What does that mean? Every time we read this xy plane, this means z equals to 0, because now we're going to describe volume. We no longer look for length and width. We're also looking for bottom and top. That is, or floor and roof. Okay, so in this case, the floor is the xy plane, z equals to 0, and that matters a lot. All right, so okay, let's plot the region of integration. Number one, that is y equals to x squared. Okay, that's the parabola. And what else? Is that it? Oh, I forgot. Did I forget anything? Looks like I forgot to type y equals to 1. Okay, y equals to 1 in the problem. All right. So y equals to 1. That's going to give us this region of integration. Let me call this R. Let's shade. Let's shade our region of integration. And okay, so that's y equals to 1. That's y equals to x squared. And of course, since in this case it says the first octant, when they say first octant, it is understood that x equals to 0, right? X equals to 0 because it's only the first quadrant. It's the projection of the first octant, if we will. So that is x equals to 0. But what is this x going to be? Okay, this should be x equals to 1 because 1 squared equals to 1. All right. Okay, so we're ready to set up this volume integral. That is v equals to the integral over the region R of the function f of x y dA. Okay. So number one, find the volume. Okay. Oh, I believe I have a GeoGebra project for this. I'll open it up in a second. Okay. So let's see. No. Not this. Let me see if I believe I do. Okay. So using GeoGebra, let me show you the solid. So number one, I'm going to put it this way so we can see the XY projection. All right. Which is what we did by hand. All right. So here, let me get rid of this surface perhaps, but yeah, this one. So this bottom right here, it's given by y equals to x squared. Okay, so and well, these curves right here that I have are actually the armor of the solid we're finding. I have this other surface that is going to describe that wall over there. This other surface that describes the other circular shape there, and the top, which is the top of the plane. The plane z equals to, what's that? It's right here. So if I put only regions like this, it would have been hard to visualize the solid over we're integrating. So well, actually, again, what's it called? GeoGebra has pretty cool functions to parameterize lines and surfaces in order to come up with better solids in here. Okay, I will actually share these GeoGebra files in our Canvas page so you can download them and see them at home. Okay, so here, okay. Oh, again, coming back to the solid. So in this case, we need to figure out what's the roof and what's the floor. So the roof is given by this diagonal plane. The diagonal plane given by this plane y plus z equals to 1. Well, here is the surface for the entire plane, but I was only interested in this portion of the plane bounded by this cylinder and not the entire plane. Okay, so the bottom, it's going to be the xy plane, z equals to 0, right? So it's going to be from 0 to whatever the equation of the plane is. So okay, so number one, this f of x y inwards, that is roof, minus floor. Those are going to be functions of x and y. So I need to rewrite this y plus z equals to 1 as z equals to 1 minus y. That is going to be a function z that depends on x and y. Well, in this case, just y, right? Okay. So what about the limits here? So that is equal to the integral of roof, which is 1 minus z, minus floor, which is 0. I'm going to go the order dy dx because the region is actually vertically simple. It is also horizontally simple, but since we already have functions of x, take advantage of the functions of x. Don't waste time changing to functions of y unless you were otherwise expected. Like write everything in terms of functions of y and set up an integral in functions of y, and then choose between the easiest one to evaluate. But well, in this case, they're not telling us anything about it, so we're just going to go about the easiest we can. Okay, so vertically simple, that means the horizontal line y equals to 1, it's always at the top of the parabola y equals to x squared. So that's why the limits are going to be from x squared to 1. And in the x direction, it's going to go from 0 to 1. All right? That equals the integral from 0 to 1, that is 1 minus z, that is simply, what's that? So 1 minus y times y, evaluated between x squared and 1 dx. Let me distribute the y from 0 to 1, that is y minus y squared, and from x squared to 1 dx, upper limit minus lower limit. And in this case, I'm not going to highlight the limits in the variable because we only have y's. If we had a combination of x's and y's, I would have highlighted them so you can see where do we evaluate this. Okay, so that's from 0 to 1. 1 minus 1 squared, that's upper limit, minus lower limit, x squared minus x squared squared dx. Let's simplify all this madness here. So 1 minus 1 squared, which is essentially 1 minus 1. Yes.
So did you take z with respect to y?
Oh, it was supposed to be... Oh no, this was supposed to be 1 minus y, not 1 minus z. Thank you. Yeah, which became this 1 minus y, right? Yeah. So 1 minus 1 squared, which is 1 minus 1, that's a 0. So we are left with wait, hold on. Okay, let me go back all the way here, all the way. Jesus. Okay, so the 1 minus y dy from x squared to 1. Okay, the integral of 1 is y. The integral of y, it's y squared over 2. Yeah, that changes the whole result, right? That's thanks to the z I did before. And that goes between x squared and 1. Okay? Upper limit, that is the integral from 0 to 1. So that is 1 minus 1 squared over 2 minus lower limit, that is x squared minus x squared squared over 2 dx. All right? Okay, let's simplify. Oh, so no, it's no longer going to be a 0. So that's a 1 minus a 1/2. That's going to be 1/2. All right? So that's the integral from 0 to 1. That is 1/2 minus x squared minus minus equals plus x squared squared. What's x squared squared? That's x to the 4th, or 1/2 x to the 4th dx. So let's integrate this polynomial. Okay, so that'll be, number 1, the integral of 1/2, that is 1/2 x. The integral of x squared, that's x cubed over 3, or 1/3 x cubed, and plus 1/2 times x to the 5th over 5 from 0 to 1. That means 1/2 times 1/5, that's 1/2 x minus 1/3 x cubed plus 1/10 x to the 5th from 0 to 1. Okay, so this one is going to be a quick one to evaluate. Well, so that's 1/2 times 1 minus 1/3 times 1 cubed plus 1/10 times 1 to the 5th minus, do you guys agree that if we substitute the lower limit of 0 to the 3 terms, it's just going to give us a big 0? So minus big 0, that's fine. You don't need to write down that 0. So that'll be equal to 1/2 minus 1/3 plus 1/10, which is equal to 1/15. Right?
4/15, right?
4/15, you got 4/15. So I get 3, 3, 2, and 2. So 3 minus 2, that's 1/6 plus 1/10. That equals, okay, yeah, so that is, it's 10, 6. So that's 16 over 60. That equals 8 over 30 and 4 over 15, right?
Yes.
Yeah. 4/15. So that is the volume of the solid bounded by this region. Okay, the next exercise. So guys, in some cases, you will be asked to only set up, not evaluate, which is the next exercise. Set up the integral that finds the volume of the solid between the plane z equals to 1. That's actually a very similar picture that we just did, but it's actually shifted 1 unit in the z direction, and bounded below by z equals 1 and bounded above by z equals to 2 minus y. Well, the other one was 1 minus y. All right? Now, the floor of the solid is given by this set right here. That is, x is varying between 0 and 1. Y is varying between 0 and this curve right here, which is 1 minus x squared. All we need to figure out here, what's the floor and what's the roof of the solid. Well, the floor seems to be this is the floor, this is the roof, right? But the base of the solid, even if it's above, if it's shifted up in, I don't know, some units along the z-axis, that doesn't matter. It will always have a projection onto the xy plane, just for reference to determine whether the region is vertically simple or horizontally simple. Well, in this case, it's a nice vertically simple region. So we could go about v equals the double integral over the region R for the function f of x, y, dA. And again, dA has two possibilities, either dy dx, that means vertically simple, or dx dy, that is if the region is horizontally simple. So we decided to go the vertically simple way. All right? So that means this is the double integral over the region R. Well, not over the region R. We can already put these regions. Actually, it wouldn't hurt actually if you change the perspective of this projection onto the xy plane. That could help us see this better. That is, bounded above by y equals 1 minus x squared, bounded below by y equals to 0. From the horizontal direction goes from 0 all the way to 1. So 0 to 1, 0 to 1 minus x squared, and in this case we need an idea for roof minus floor. Let me go dy dx, where the roof is given by the equation of the plane, 2 minus y, minus the floor, which is 1. All right? So let's simplify this integrand. That is the integral from 0 to 1, and then from 0 to 1 minus x squared. 2 minus 1 equals to 1 minus y dy dx. And in this case, they're not asking us to evaluate the double integral to compute the volume. Just set it up. All right? Just set it up. All right. What's next? Let's see. Average value. Okay, so you might remember the average value of a function from calculus 1. That is, you evaluate the double integral and multiply by 1 over b over a. Well, what is that 1 over b minus a? Because this b minus a represents the length of the interval over your integrating. So you are defining the value of the area by the length to get the average value, like in statistics to find the average or the mean, depending different ways to say the same thing. But I mean, visually, what is this? Well, let's call this f bar, f with a bar. The bar means average, right? So what's the picture here? Okay, that means, so you consider this planar region, all right? Over the interval A and B, all right? So that's going to give us some area, all right? Okay. Now, suppose that region is, I don't know, maybe peanut butter, all right? Let's suppose that's peanut butter on a table. So then what are we going to do? We're going to, let's get a knife. And turn this region into a rectangular region. That is, I'm going to use my knife and move this down and move this up. All right? And turn this into a rectangular region. Okay, oops. So that's going to look like this. From A to B. And I'm going to end up with this rectangle. Well, it looks almost square. It could be a square. It could be a rectangular. So this is what happens. So when I get a knife and fix this peanut butter region, I'm coming up with an average value in between. All right. So this average value, which is going to be, it's going to be this height right here. So let me call this again f bar. So what does the average value mean? Well, that means this result f bar, it's the height. I need to set a horizontal line so that the area under the curve is equal to the area of the rectangle. All right? So that's the idea behind the average value from a geometric point of view, if you will. Now, how do we take this to the three-dimensional setting? Well, so the average value of a function for two variables. So we're going to evaluate the double integral, of course, but instead of multiplying by 1 over b minus a, because again, b minus a represents the length of the interval, okay, that's the length of the interval. What else? Because we're adding a second, we're going from the first dimensional setting to the second dimensional setting. Well, the idea of a second dimensional setting is no longer length, it's area, right? So we're going to divide by the area of R. And well, this calculation, guys, if our region of integration, it's a nice and an easy rectangular region, just use geometry to compute that. But if it's not a rectangular region, then we would have to set up a double integral first of all to find the area of that region, and then also evaluate this double integral that contains this f of x y function. Okay, so how do we look at this visually in space? Well, let's evaluate. Let's have a look at this example and then evaluate and then see this visually. Find the average value of the function f of x y equals to xy over the region R, where R is a rectangle in the xy plane with vertices at the origin 2, 0, 2, 3, and 0, 3. Number one, let's plot that region of integration. Okay. All right, so that'll be, so 1, 2, 3, 1, 2, 3. Okay, so we're going to go about 0, 0, 2, 0, 2, 3, 0, 3. Okay, so that's going to be this rectangle here. Let me call this R and shade. So, number one, our domain of integration, R, is given by this set, X, or described by this set. All the order pairs, X, Y, such that X is varying between 0 and 2, and Y is varying between, what was that, 0 and 3. Okay, oh, don't forget to close this set. Alright, so we want to find the average value, f bar. Okay, let me call this f bar, or z bar if you will, doesn't matter, f bar, z bar. So this will be given by number one, 1 over the area of R times the double integral of the function f of x y dA. So this is in general how we would find the area of that, the average value. Well, in this case, since the area or the region of integration, which is R, it's a nice geometric shape. What's the area of that? 2 units by 3 units, 2 times 3 equals to 6, right? So this is f bar equals to 1/6 the integral from, okay, in the x direction, so dy, in the y direction, dy dx to xy. So the y direction goes between 0 and 3 and between 0 and 2 for the x direction. this integral is relatively simple to evaluate, but let's go about the process, okay? So that'll be number 1/6 times the integral from 0 to 2, integrating with respect to y. That's going to be y squared over 2 times 2x, which is really xy squared from 0 to 3 dx. And again, these limits of integration are going to be simply for the variable y. So careful when computing the result. So this will be equal to 1/6 times the integral from 0 to 2 x times y squared, which is 3 squared minus 0 squared dx. Okay, 3 squared, which is 9, minus 0 squared, which is 0, that's 9. 9x, I'm going to take this 9 outside and multiply with the 1/6, 9/6 integral of x dx from 0 to 2, 9 over 6. Is that 3 halves? 3 halves. The integral from 0 to 2 x dx, which is 3 halves x squared over 2 from 0 to 2. Okay, that equals 3/4 2 squared minus 0 squared. Okay, what is that? 2 squared minus 0, is that 4 over 4? Is that equal to 3? Is that equal to 3? Okay, but what does that mean? I mean, because we're not doing anything different in terms of the computations, right? Just adding that 1 over area of R factor, but other than that, we're doing the same thing. The visual, I mean, how do we... What's the 3D version of this peanut butter idea in space? Well, okay, where's my... So this is the solid represented by the double integral, or by the problem we just computed. So it's bounded below by z equals to 0. That's the floor. Here we have this roof that looks a lot like like a pyramid. It looks a lot like a pyramid, but I mean, this is the function y equals to 2xy. That's given by, where is that surface? That should be this one, maybe. Yes, that's this surface. All right. Let me actually do it again. I won't be able to type it anyway. So let me see if I can. Oh yes. So let me do z equals to 3. Okay. C equals to 3. What is that? Which is the value we got. So in the 2D setting again, I'm finding an average value for which the area under the curve is equal to the area under the rectangle. Here, if you think of a solid, do you see this portion of the solid above the plane? So if you put all this solid outside here, it would fill in, and we would come up with a rectangular box. So that is, in other words, the volume of the shape is equal to the volume of the rectangular box, whose height is what? 3 units. So all this volume, believe it or not, all this volume right here that lies at the top of this horizontal, well, in our perspective, horizontal plane should fit in this empty space right there and fill in a rectangular box. Right? It's like doing the peanut butter, but in 3D, like a pizza dough. You know, you have like a spherical pizza dough, but you want to turn it into a perfect rectangular box. That's the idea behind the average value. All right. And what's next? So we got this exercise. I think